Hello, my name is Jason Sanders, and I'm the CTO and co-founder of Transient Plasma Systems. Thank you for joining me today for this presentation that gives an overview of my team's work to develop a high-power, ultra-fast closing switch for ultra-wideband directed energy applications. As we'll discuss in this slide deck, this switch is enabling technology for the development of compact, long-lived systems capable of generating intense and repetitive ultra-wideband directed energy for electronic warfare applications. Before we get into the details of this work to develop this capable closing switch, which is commonly referred to as a semiconductor avalanche shaping, or SAS switch, let's take a minute to review Transient Plasma Systems, who we are and what we do. Transient Plasma Systems, or TPS, was founded in 2009 by members of Dr. Martin Gunderson's Pulsed Power Group at the University of Southern California in response to a perceived need within DoD and other entities for compact, solid-state pulsed power systems. The core team that founded the company has well over 100 years combined experience in the field of pulse power and plasma science, and that number has grown as our team and facilities have expanded. TPS currently occupies more than 12,000 square feet of office and manufacturing space in Torrance, California, just one neighborhood over from LAX. Since its founding, TPS has designed and manufactured advanced pulse power systems, developing a line of products and continuing to innovate with custom solutions for customers, including DoD, DOE, private businesses, and industry partners. Over the last 5 years, TPS has developed internal expertise designing and manufacturing custom semiconductors designed specifically for high-power pulsed applications, which has enabled significant improvement in performance and reduction in size. TPS is leveraging this expertise for this program, in which TPS is currently manufacturing its first run of SAS closing switches, which will ultimately be capable of radiating megawatts of pulse power with spectral content from low frequency up to the S-band, or approximately 4 gigahertz. The Office of Naval Research has been funding science and technology research and development efforts to identify wideband and ultra-wideband solid-state technology to enable new approaches for developing compact, high-power systems for directed energy applications. In 2020, TPS responded to a solicitation seeking development of a sub-nanosecond semiconductor switch to improve the performance of high-power microwave systems by extending the bandwidth of solid-state pulse generators. To address this challenge, TPS proposed and is currently developing semiconductor avalanche shaping, or SAS, closing switches. These relatively simple two-terminal devices sharpen the rise time of an incoming broadband pulse to achieve a 10 to 20 times faster wavefront. Without worrying about the physics of impact ionization within the switch or the circuits that make it switch so rapidly, you can think of it as a high-voltage, high-current switch that can transition from open to closed about 50 times faster than modern semiconductors used in advanced power electronics circuits. As TPS is working with ONR and other stakeholders in the DoD pulse power community to develop and mature this megawatt, ultra-fast switching technology, other potential customers outside of Navy, including Air Force, aerospace companies, and companies working in other industrial spaces, have expressed interest in the technology and its future development. The switches TPS is developing will enable a new class of robust, high-power, highly repetitive ultra-wideband pulse modulators for directed energy applications for Navy and DoD. And, as the technology matures, it is expected to serve both ground-based and air-sea applications. TPS is working closely with the stakeholders of this effort to ensure the success of the program and the devices that are being made as part of it. TPS has worked with this team at ONR and NRL, the Naval Research Laboratory, since 2018, initially working to successfully develop a broadband opening switch referred to as a drift step recovery diode, or DSRD. Work done on that device, which TPS was able to make switch more than 3 times faster than previously expected, has resulted in a commercial product that is expected to be part of a program of record in 2023. To radiate highly repetitive, high-power, ultra-wideband impulses up to the S-band efficiently and reliably, a solid-state switch capable of blocking tens to hundreds of kilovolts with a rise time faster than 250 picoseconds is required. TPS is developing an SAS to meet these specifications. The device designs are custom, but the device TPS is currently making uses established semiconductor processing techniques, enabling more rapid development. TPS is currently designing SAS parts using a process that largely overlaps with the more mature process that TPS has already developed with internal R&D investment. 100 kilovolt switching may be a lot higher than people are used to hearing in conversations about solid-state devices. TPS has developed a bonding process for its pulsed power devices that allows direct bonding at the wafer level so that parts can be made of multiple series stacked wafers to achieve greater voltage blocking capability. The final parts, consisting of bonded wafers, are packaged in a way to enable additional stacking at the component level to further increase the total voltage blocking capability. This stackable design enables these high voltage switches to be installed as if they are a conductor in a broadband transmission line or antenna. This form factor enables them to maintain high ultra-wideband performance. TPS began work on Phase 2 of this SBIR program in January of 2022 and is collaborating with Dr. Reza Gandhi at GE Research. GE provided simulation support during the design phase for this device and will continue to perform simulations to compare against measured results collected when lab bench testing of manufactured parts commences. GE is also researching the design of a silicon carbide SAS switch and is currently in planning phase for manufacturing the initial silicon carbide SAS parts. TPS is midway through the manufacturing process of the first batch of TPS silicon-based SAS parts. Based on the work done to this point and previously published peer-reviewed articles, TPS believes that the stackable silicon SAS parts will provide a near-term solution for a mission-critical need to field reliable, compact, ultra-wideband pulsed systems and radiation sources. Silicon will hit the baseline specs outlined by Navy. However, TPS believes that wide bandgap materials like silicon carbide are likely to provide superior performance, including reduced size, increased power density, higher temperature operation, and faster switching time for the next generation of pulsed power closing switches that block tens to hundreds of kilovolts and switch ultra-wideband pulses into the S-band and beyond. This Phase 2 base R&D effort will result in TRL-5 ready devices that will have been evaluated at TPS and can be tested in DoD systems in need of SAS-type closing switches. A potential Phase 2 option R&D period will be valuable to fine-tune the performance of silicon SAS switches and further mature silicon carbide SAS switch design. As discussed in previous slides, TPS expects this technology will add new capability for Navy and DoD directed energy applications that require reliable, high average power, highly repetitive, ultra-wideband pulse generators capable of switching pulses at megawatts and potentially even gigawatts level power. Please take a moment to look at the table below, which intends to highlight trade-offs between different technologies used to generate ultra-wideband radiation. TPS is working with ONR and other interested parties to continue development beyond the Phase 2 base and into a Phase 2 option. This Phase 2 work is ONR-funded science and technology, and additional resources are needed to further develop and mature SAS technology. Work on the Phase 2 base is on schedule, and TPS is interested in reaching out to primes and other potential industry partners. TPS is working with Mr. Ryan Hoffman at ONR to identify additional opportunities to continue developing SAS and DSRD technology for compact, wideband, and ultra-wideband sources. TPS is also engaging with other DoD agencies and aerospace primes to understand their needs and interests. If this switching technology is of interest to you or your colleagues, please feel free to reach out to TPS points of contact listed in the final slide of this deck. We'd be happy to tell you more about this work and learn more about your requirements. Looking beyond DoD requirements and considering potential dual use cases for this technology, TPS has identified some application areas that may benefit from this technology. Since its founding, TPS has collaborated with dozens of established companies across multiple industries to work toward commercializing pulse power systems. Applications include clean combustion, pollution abatement, and biomedical. Biomedical has a number of potential applications, and the picosecond switching capability of SAS make non-invasive internal electroporation a good target to initially explore. Additional opportunities also include plasma processing applications that benefit from the generation of high-energy electrons enabled by high-voltage, fast-rising pulses, like those generated by a DSRD and SAS switched system. The diagram below illustrates anticipated benefits for plasma applications that will be enabled by increasingly short-duration pulses. Two other application areas where TPS has shown benefits from short-duration, high-power electrical pulses are advanced ignition and fuel-burning engines, and pollution abatement of particulates in exhaust. TPS has worked on developing pulse power systems for these applications with industry partners for over a decade. Taking advanced ignition as an example, TPS's ignition systems, which are based on TPS high voltage nanosecond pulse generating tech, offer a key value proposition of up to 20% improvement in fuel efficiency, up to 20% reduction in CO2 emissions, and greater than 50% reduction in NOx emissions. These improvement gains are enabled by TPS's advanced ignition systems capability to extend flammability limits within an internal combustion engine, enabling more thermally efficient operation. TPS has successfully tested its system with several leading car and engine manufacturers across the world. Although the automotive industry is difficult to penetrate, TPS continues to work with its partners to develop a commercializable version of this technology. Penetration of TPS advanced ignition technology into the automotive market alone is estimated to be worth $17 to $20 billion. As TPS continues to identify potential commercial dual-use SAS applications, we are also working to identify DoD agencies and/or primes interested in the maturation of this technology. In 2023, TPS is working to identify a party interested in working with ONR to cost-share Phase 2 option funding for this effort. Additional funding resources both at the device and system development side will help to improve the United States ultra-wideband technology portfolio. Thank you for taking the time today to listen to my presentation. If you or any of your colleagues have any interest in the technology discussed in this talk, whether for DoD or other applications, or in solid-state pulse power systems in general, please feel free to contact TPS using any of the emails displayed on this slide. I'll pause here so you have time to snap a photo. Thanks again for taking the time to learn more about TPS.